This conference will now be recorded.
Good evening, students. We have come again for the discussions of the question paper 4th April 2024 shift to JEE Mains. So we had remaining few questions from this particular paper, and then we have picked up few more questions from 5th April's first shift paper. Okay, so let us start our discussions. Let me change the color. Okay, now let us read the question first. The question says a heater of rating 50 watt 200 volt is connected with the source voltage 100 volt. Power consumed by heater is how much? Okay, so you have to find out the power consumed by the heater when the heater is connected with the source of voltage 100 volt, and see the power rating for the heater is given. So 50 watt 200 volt is the power rating. That means, power is 50 watt and voltage, okay, is this one. That means when the voltage across the heater is 200, then the power consumed by the heater will be 50. Now if we want to find out what is the power consumed by this heater when it is connected to 100 volt source, then we need to find out from the given information, we need to find out the resistance of the heater, okay, heater coil. Okay, so let me write power in terms of resistance. I can write either I square R or V square by R. I'm using this formula because voltage is given. So from here I can find out what is the resistance of the heating coil or the heater, so that we can find out using this formula. Okay, so this is 50 watt. Now same formula I'll be using to find out the power. Let us say that is P1, and this is V1 square by R. So V1 is given as 100. This is R means 200 square by 50. That's 50 will go to numerator, and this will be in watt. Okay, look this. So I have got 50 by 4, right? So this will give you, see this, I can write 25 by 2, that means 12.5 watt. So option D will be the correct answer for this question. So these were actually very simple questions. You should not take this much time. You can directly write this formula and do the calculation within 30 seconds maybe. Okay, let us go to the next problem. With regard to gravitational parameters, the dimensions of t square are same as that of. See the options here. G is the universal gravitational constant, R is the distance, and this m, let us say that is the mass of R. So in these three terms, like which expression among these four, or which quantity among these four will give you the dimension of square of time? Okay, so to get that, let me write down the gravitational force that has got dimension of force anyway, and see that we can write G M. M is the mass of the earth, and suppose there is a mass of like an object of mass small m, and at a distance r square from the center of the earth. Okay, so this will be the gravitational force on that, right? Now I have quantity gm by r square, rq, etc. Let me check what is the dimension of this particular quantity. So gm by r square has got dimension of a by m, that means dimension of acceleration. Acceleration is L t to the power minus 2. See, F by m, force by mass is acceleration, right? So this is L t to the power minus 2, right? Now I have to get dimension. So I have to get dimension of t square. Let me write this as L by t square. Okay. So t square by L could be r square by gm, this one. Then if I have to get t square dimension, then I have to multiply 1 r here, so that it becomes t square, right? Dimension of t square. So what we get? R cube by gm. Dimension of this particular quantity will be only t square. Okay. So look, the first option, r cube by gm. This will be the answer for this question. Okay, this was also very simple question. Okay, so this is from semiconductor diode. Okay, so which of the following circuits would have the diode in conducting state? Conducting state, we know diode. So this is n side and this is p side, right? And diode will conduct when it is forward bias. Forward bias means this will be having comparatively higher positive potential, and this will be in the lower positive. If positive, at least it has to be forward bias, that means positive. If you just use battery, positive terminal has to be connected here and negative terminal has to be connected here. Okay, if okay, let us see that things over here. So I have to find out which one is forward bias. So this is not a forward bias, this is actually reverse bias, right? So this is not going to conduct. Look here also, this negative is connected here, so this is also reverse bias, so this is not going to conduct. An ideal diode. Look this one, this is B. Okay, look this one, this is actually positive terminal, so this is actually forward bias. Okay, forward bias. What about this one? This one is again, see, again this is reverse bias. Okay, reverse bias. So option B, this one will be the conducting diode. Okay, so here in this circuit I can say that diode is in conducting state. Okay, conducting state. All right. Okay, so here is another interesting problem. The problem says 2 point masses m and 2m are on the straight line. I'm sorry. Okay, so m and 2m, these are on a straight line. Let us say this is along the x-axis, say. Okay, this is m and this is 2m. If mass M moves towards the center of mass by distance 2 centimeter, the distance mass 2m should move. Okay, so mass move so that center of mass does not change. Okay, so let me just take this one. This one is small mass, right? So if I know that this is x1 and this is x2 coordinate, okay, then I can easily find out what is the coordinate of center of mass. How? M x1 plus 2m x2 divided by m plus 2m, like this, isn't it? Now look, if this x becomes, suppose x1 becomes 2 centimeter somehow, okay, then how much should be x2 such that there is no change in this? Okay, what is, there is no change in this? Okay, that means, look, let me write this. So suppose m into x1 is 2 centimeter plus 2m into x2, which I have to find out, divided by 3m, and this is actually giving you, suppose, zero displacement. Okay, zero displacement of the center of mass. So from here we'll be able to find out what is the x2. Okay, then I can write 2m is equal to minus 2m x2. So this 2m cancels out, and what we get, x2 I get as minus 1 centimeter. That means what? If the mass small m moves, see, generally center of mass will be situated somewhere near to the bigger mass or bigger mass distribution. Okay, so suppose this was COM. Now this guy has moved up to 2 centimeter over here. Okay, like at this position, then this mass also has to shift. So if this shifts this way, okay, then to keep this center of mass at the same position, it has to actually move in the opposite direction and by half of the distance. Okay, half of the distance, that is 1 centimeter. Okay, that is 1 centimeter. So if this mass moves 2 centimeter, then this has to move 1 centimeter. Okay, all right. Now this question says a body of mass 4 kg is at a height of r, that is the radius of the earth from the surface. Okay, radius, see, I'll just tell you here how it is. So the weight of the body you have to find out. Suppose this is the earth, it has got radius capital R, and there is an object which is exactly r distance away from the surface. Okay, so at this position, suppose P, what will be the weight of the body? the mass of the body is given as 4 kg. So what we have to find out, we have to find out what is the G prime over here, right? So we know the formula whose height is G r square by r plus h. Sorry, this, if I say this is height small h, if I say this height is small h, then this, okay, here this h is given as r. So what is G prime then? G r square divided by, see, r plus r 2r whole square, right? This will give you G by 4. Okay, G by 4. G prime is G by 4. Then what is the weight? Weight will be 4 into G prime. That means what? 4 into G by 4. This one, that means, you know, this is becoming equal to G. And if I say this is force, unit of force, so if I take G as 10, so this will be 10 Newton. Okay, so this will be 10 Newton. All right. Okay. Now let us go to the next problem. So this is a problem from bar magnet. A bar magnet of magnetic moment 0.5 ampere meter square is under the influence of magnetic field 8 Tesla. Find the work done to move a magnet, the magnet from stable to unstable equilibrium. So to solve this problem, we need to know what is the position of stable and what is the position of unstable equilibrium. Okay, stable and unstable equilibrium. In case of electric dipole moment also we had seen this kind of question. So whenever there is a magnetic dipole having magnetic moment mu is placed in magnetic field and rotated by an angle theta. Suppose I have magnetic field in this direction and I have my magnetic dipole or the bar magnet at a certain angle. Okay, this bar magnet has magnetic moment mu at certain angle theta. So at this position, you know, what is the potential energy? Potential energy at this particular position u theta can be written as minus mu b cos of theta. Mu b cos of theta. Now suppose, okay, so what is the stable and what is the unstable equilibrium? Stable equilibrium, at stable equilibrium, the potential energy will be minimum. Okay, potential energy will be minimum. So look this expression, when this potential energy will be minimum, potential energy will be minimum when theta is equal to 0 degree. Okay, that will give you minus mu b potential energy. Now second point, what is unstable equilibrium? At unstable equilibrium, the potential energy will be maximum. Actually, total energy also I can say, but here I'm talking with respect to potential energy because there is very negligible kinetic energy I can say, or maybe zero kinetic energy you can consider. And obviously, even if you rotate the dipole, the kinetic energy is not going to change. Only thing which is changing is the potential energy. So that's why I'm talking with respect to potential energy. Okay. So when this potential energy will be maximum, look, this I say mu1, sorry u1. Let us say this one is u2, and that is happening when theta is equal to pi, and then the potential energy will be mu b plus mu b. This is the maximum potential energy, right? And that is where the unstable situation. That means this is stable. If I say this is mu and this is the direction of magnetic field, when the magnetic moment or the bar magnet is along the direction of magnetic field, then it is in stable equilibrium, stable. And if the magnetic field is this way and the magnetic moment or the bar magnet is placed in this fashion, then it is unstable. Okay, unstable equilibrium. All right. Then what will be the work done? The question is, find the work done to move the magnet from stable equilibrium to unstable equilibrium. So what will be the work done? How to find out the work done? Let me just erase this. Okay. So I have got theta 1 stable condition, sorry u1 stable condition minus mu b, u2. Okay. So let me write this as theta is equal to 0 degree. And this is pi, or 180 degree I should write when I am writing in terms of degree. So this is mu b. That means you have this magnetic field. I had initially the bar magnet in this direction. I have to rotate all the way in this direction, right? In this direction. So I have to rotate by 180 degree. So what will be the work done? And work done is actually the change in the potential energy. Change in the potential energy. So what will be the change in the potential energy? That is u2 minus u1. So u2 is mu into b. This is mu into b, minus of minus mu b. This is 2 mu b. See, I am doing this very rigorously just to make you understand, but in the exam, when I'll be writing in the exam, I'll just write this formula, just this one. Even I'll not write the formula, I'll just directly write work done is equal to 2 mu b. Okay, 2 mu b, 2 times of mu b. So what is the value? 2. What is mu? That is 0.5 ampere meter square. And what is this? Mu on m is same thing. Magnetic field is 8. So what we get? We get 8.0 joule. Okay, 8.0 joule. All right. So this is the answer actually. Okay. I think there was a dash over here. Dash joule. Okay, dash. Work done in joule will be dash. So this is actually 8 joule. So work done will be 8 joule. Okay, let us go to the last problem for this, like last problem from 4th April paper. So this problem is really interesting problem. I'll explain you a little bit. See, there is a methane molecule, methane, CH4, 1 carbon and 4 hydrogen. You can see that this is C, these are H. So this has a nice diamond structure in the 3 dimension, right? Like this, like this. Okay. What is the question? Question is the translational degrees of freedom is F1 for this methane, while rotational degrees of freedom, for the methane is F2. Let me tell you what is rotational and what is translational degrees of freedom. So let me write F degrees of freedom. Okay. Degrees of freedom. See, degrees of freedom has got a formula 3n minus L. Okay. So what is 3? 3 is the dimension. What is n? N is the number of molecules. Sorry, number of atoms present over here. Okay. And L is the number of constant. So if we apply this here, see I have 4. So 15 minus how many? 1, 2, 3, 4. 4. Something 11 degrees of freedom I can see. Okay. 11 degrees of freedom. But this is total degrees of freedom, you know. In this, there will be translation, there will be rotation, there will be vibrational also. Okay. So here we will not go with this formula blindly. We'll see what are the informations given in the question. What informations are given? Informations are given that there are translation, DOF, that is given as F1, and rotational DOF is given. F2. See, at low temperature we will have only, see, below, when temperature is below 100 Kelvin, only translational degrees of freedom will be there. T translational DOF will be there. Okay. Then temperature between 100 to 1000 Kelvin, there will be both T plus rotational. Let us say this is T plus rotational degrees of freedom R. DOF R. So we'll have in this range of temperature T plus R, both degrees of freedom will be there. But when the temperature is much greater than 1000 Kelvin, then vibrational degrees of freedom will come. Vibrational DOF will be there. Okay. Now for this they have told just translational and rotational degrees of freedom will be there. So better not to worry about this vibrational degrees of freedom, and neither I'll be thinking of what temperature and all. We have been just given rotational and translational degrees of freedom. See how many maximum translational degrees of freedom we can have for any object in 3 dimension. In 3 dimension, see this object, if I move this object, this can be moved in this direction, and also along this direction. So along three mutual perpendicular directions, that means along x direction, along y direction, along z direction, I can move this three-dimensional object. This shape, see, this is the molecular structure of methane. So methane can be moved any three direction, okay? Along any three direction. So degrees of freedom, translational degrees of freedom will be 3. What about rotational degrees of freedom? See, rotational degrees of freedom depends on how many rotational axes it can have. That means how, in which way it can rotate. See, it can actually rotate in this way along this. If I just have rotational axis like this, then I can rotate in this horizontal plane, right? So that is one rotational degrees of freedom. If I have axis of rotation in this way, so I can rotate about this also, okay, about this axis, and I can take another perpendicular axis along that also. I can rotate this three-dimensional object, okay. So I can say clearly that methane can have maximum 3 rotational degrees of freedom, right? See, let me give the axis. See, if I take just horizontal axis, it can rotate about this, okay. I can have an axis. Let us take this as perpendicular axis, okay. This I can have one axis, and another axis is this. These are two in plane, and look, this is another one vertical, okay. So I can have 3 translational and 3 rotational degrees of freedom, okay. In 3 dimensions, this many maximum I can have. So what will be then f1 plus f2? This is what we have to find out, right? F1 plus f2, that will be 3 plus 3, that means 6 degrees of freedom, okay. So this will be, see, f1 plus f2, the total number of degrees of freedom including translation and rotational degrees of freedom, that is number 6, okay. There will be 6 degrees of freedom. All right, okay. Let us go to the next problem. This is an interesting problem. The ratio of radius of gyration of uniform hollow sphere and uniform solid sphere about its diameter, both have the same radius, you can take. That means suppose I have a hollow sphere having same radius, let us take that as capital R, and I have a solid sphere, okay. Solid sphere, this also has radius R. So let us say hollow sphere HS and solid sphere SS. We have to find out ratio of gyrometric, sorry, um, radius of gyrometric ratio, okay. Ratio of radius of gyration, okay. Ratio of gyrometric, sorry, radius of gyration. I'm sorry, radius of gyration. How do you find out the radius of gyration? If I say k is the radius of gyration, then I have to write mk square is equal to the moment of inertia of the object. So in this case, I have to find out radius of gyration for hollow sphere. So this I can write moment of inertia of a hollow sphere. So moment of inertia of a hollow sphere about its any diameter is given as any diameter, it is given as 2 by 3 m r square. Okay, let us write that 2 by 3 m r square. This m are the same, so I get KHS is equal to square root of 2 by 3, and this is r. Okay. What about solid sphere? We know solid sphere moment of inertia. So this is where actually people will be stuck up. If you don't remember what is the moment of inertia of a solid sphere, about its diameter, then things are not going to move. You need to actually know this formula. And for a solid sphere, we know 2 by 5 m r square. Okay. So according to this, I can write KSS is equal to square root of 2 by 5, and r will be outside of the square root. Now I have to take the ratio of radius of gyration. This sometimes people say radius of gyration. So this is 2 by 3 and this is 5 by 2. So this 2 will cancel each other and you'll get the ratio 5 by 3, square root of 5 by 3. So this is actually the answer, and look, this option B will be the correct answer for this question. So what my advice is that please you remember the moment of inertia of uh, various symmetrical object like cylinder about its own axis, about an axis, like axis passing through the passing through the perpendicular bisector. Okay, like that. Then can be, so this is solid cylinder. You can, like, question can come from hollow cylinder, then cone, moment of inertia of cone. Okay, hollow cone, solid cone, etc. There are few standard geometries for which you must remember the moment of inertia, so that in the exam hall you don't have to spend a lot of time to solve this kind of problem, and you will get full marks also. Okay, so I think there is no much difficulty in remembering various, like, moment of inertia of various symmetries like cone, cylinder, hollow sphere, solid sphere, then ring, then you have disc, spherical shell, etc. So those geometries you should remember the moment of inertia about their diameter and about their about the own axis. Okay, all right. Let us go to the next problem. Okay, so what is this problem saying? Okay, this problem actually we have already uh, started with the 5th April shift 1. I see. So this will be shift 1 paper, actually shift 1. So 5th April shift 1 paper. The question says, if the time period of a pendulum at height r, where r is the radius, from the surface of earth is t1, that means some person has gone with a pendulum up to r height from the earth surface. So this is suppose r height from the earth surface. So this height, at this height, he has measured the time period of the pendulum to be t1, and then he has moved, later he has moved to a height of 2r from the earth surface. Earlier it was r, now it is 2r from the earth surface. So what will be the time period? We have to find out, and I have to, okay, so we have to see the relationship between T1 and T2. Okay, how T1 and T2 are related, we have to find out that. So it is very simple, you know, time period of a pendulum is 2 pi root over L by G. Okay, L by G. So this is, let us say, T. Then what will be T1 at this particular R height? What is T1? Let me write this formula somewhere else. This is on the earth surface, okay? When the object is, sorry, pendulum is on the earth surface, then the time period is equal to 2 pi root over L by G. L by G. Okay, that means, you know, time period of a pendulum is proportional to inverse square root of G, like this. So I can write here T1 is 2 pi, length is not going to change, L by G prime then. Okay, so in terms of T, we can find out in terms of T. So G prime, just few minutes back we have written, this will be R plus H whole square. So G, H is given as R, right? So this will be GR square by 4R square. So R square cancel each other. So what we get? We get G by 4. We get G by 4. Okay. So if we put this value, then what I get? T1 as 2 pi root over L by G prime. In place of that, we'll write G by 4. 4 will go to here. So what I get? 2 into T. T1 I am getting as 2 times of T. Similarly, when the pendulum is taken to 2r distance away, or 2r height, look, I can just put the value of r over here. This is 2r. Then I will get G prime is equal to G by 9. Like this I'll get. Okay, now look, if I put this here at G prime at this particular position, so I'll get T2 is equal to 2 pi root over. Okay, so this is actually 2 times, so this will be 3 times. Okay, 3 times of T, 3 times T. So from these two relation, what I can write? I can write the T1 by T2 will be 2T by 3T. Okay, or T1 is equal to 2T2 and this side is 3T1. So 3T1 is equal to 2T2. Actually, I am doing it very slowly so that you can understand. But this calculation can be done by 6 seconds. Sorry, 60 seconds. Sorry, 30 seconds to 25 seconds to 30 seconds. Maybe you can take hardly. Okay. So option A will be the correct answer for this question. Okay. Now let us go to the next problem. Okay, so this is not a problem as such, this is just an information. A point source of light is placed at a focus of convex lens. So I have a focus, so a convex lens, this is the principal axis. Suppose this is the focus. If I keep a point source over here, then what is the shape of the wave front? What is the shape of the wave front passing after passing through the lens? See, what we know, if light refracts or come like incident from the focus, then the light will be actually parallel like this. Parallel means what type of wavefront you see? You see plane wavefront like this. Okay, like this you see plane wavefront like this. Okay, so question was, what is the shape of the wavefront after passing through the lens? It is actually this planar wavefront. Okay, I think this was all for today. We had quickly solved uh, some 10 or 12 questions today. We'll take up like that. We'll take up more new numerical problems or the more questions from JEE Mains 2024 April and both the April and January sessions. So we are now solving the questions from the April session, and we could see the questions are really very easy to solve. At least 5th and 4th April papers were really easy papers. Okay, like okay, so we'll stop it here for today. In the next class, we'll take up further questions from 5th April shift 1 paper. Okay, and also we'll try to get some questions from the shift 2 paper on the same day, 5th April. Okay, so thank you for your patience. Bye for today.